I already talked to many of you during the exercises, so just a reminder, the project 2, it's time to think about project 2, particularly if you pick one of these quite exciting projects from this group of 30, or perhaps even you're thinking of trying to find something on your own. It might take time to get the data, to get the agreement, so it's good to get started. The other thing is, it's of course great that you put some work into the project. Don't go completely crazy, okay? Sometimes people just, they're like 0.0000 away from like one position up, and then they spend like 300 hours and ignore everything else, okay? This is worth 30% of the grade, and there are other things also to do, and spend some time. Of course, it's great to get, to somehow trying to do something better and improve and maybe be competitive, okay? But there is also a limit, okay? Sometimes people then just ignore everything and then they have trouble somewhere else. Also, don't forget that so far, the exercise been have a lot of course about specific, code snippets and so on, things that you can use for the projects. The exam, which is counting 60%, is quite different. On the 19th of November, we'll have a mock exam. We'll just give you one, so that you see what this looks like, okay? We'll have time to fill out. And then later on, we'll give you, I think we have 2 or 3 exams from the past, and you will be able to look at these exams to see what it looks like and, to get a little bit used to this. And we'll try also to add a few more kind of theoretical prompts or prompts of understanding that's similar to what the written exam is about in the homeworks. Okay, so the final exam will look very different from what you have done so far, because there are really two parts. One is trying, being able to implement things. Another thing is to understand things, explain things, etc. Good. So last time on Tuesday we talked about support vector machines. So let me just repeat maybe in 1 minute. So what was the support vector machine? Again, it was some classification task. And again, we did it by some hyperplane, but it was slightly a different criterion. And the criterion was that given the n data points, what you tried to minimize was the following cost function, 1 minus y n x n t w, and then this was plus. So this was called the hinge loss, and then we still had a regularization term which had to do with the norm. And now this, when you look up in the literature, there's several formulations of what's called support vector machines. There's something called hard margins. And something called in particular also soft margins. So what he wrote down has to do with the soft margins. So this works, this formulation makes sense no matter what data you give me. The data doesn't have to be separable, right? Doesn't have to be linearly separable. This makes sense. You simply pay some price if things are on the wrong side or within the margin. The interpretation, though, is slightly easier for these kind of hard margin case. And so that's what I tried to explain last time by just simply saying that this is very small. So let me just repeat it. So let's assume that, but you have to, for this interpretation, you have to know that the data is separable. Otherwise, it doesn't make sense. Okay? So let's assume that you insist, so the data has to be separable, that you insist that you're only allowed to use hyperplanes that are really separating. Okay? So it has to be something where everything is on the right side. And so one way to think about it is simply to saying that here, you just make this very large, right? So one thing is to think about that this is very small, everything relatively speaking, or just think about it that any violation here just gives you infinite cost. Okay? That's why it's called hard margins. You're not allowed to violate anything. Okay? And so if that's the case, then really the only term, okay, for, as long as we have something that's separating, and as long as we're picking this W such that the margin that nothing is inside, okay, then the only thing that matters in the cost function is this one here, right? And if that's the only thing that matters, then we want to pick this as small as possible because we want to minimize this one. So this means we want to, as we explained, this is 1 over the magnitude, so we want to make that as large as possible, right? And so that's really where the interpretation comes from. And in particular, you will always extend it so that eventually on the boundary, there must be at least 1 point. Otherwise, you could extend it further. And then these are exactly what's called the support vectors. These are the ones that kind of support these margins. That's where the name comes from, okay? But of course, this only makes sense if the data separable, which typically will never be separable, or you probably won't be that lucky. And so so this is just more a thought experiment, or a kind of why you want to do things, or maybe a justification. But really, of course, the more interesting case is if in general this will not be separable. Okay, it might be somewhere here, and there might be points here. And so then this formulation, of course, makes sense also in this more general case. Then you don't have exactly the formulation because you have exactly this interpretation because you have the two terms. But if lambda is very small, then basically the first thing is that you can't have any error on the left, okay? And then you basically get back to this interpretation, right? But once you make lambda larger and larger, this term will also play more and more role. And it won't be exactly that you want to just maximize this, because there are many terms that will give you contributions, and there will be a trade-off. Okay, so that's what we did last time. Now, in particular, one thing that we did last time, we wrote down also a formulation in which what we had to look at, or in which the maximization that we had to perform, the data only entered in terms of what's called the kernel. Okay, so there was the only thing in the alternative formulation the only way that the data entered was in form of the kernel, right? And so we had x times, so x again is d times n, and then transposed, and this was d times n. Okay, and so at the end, this was an n by n kernel. And so the formulation only depended on that, and we said that that was important. Okay, and so we'll get back exactly to this point of view here. We'll look today at, there are basically 3 points that we want to do. We'll first of all show that there are many other problems. We'll just look at one, but there are many other problems that can be formulated where there are alternative formulations. We have seen this already, right? For least squares, right? We have seen just the geometric interpretation. We have seen the interpretation in terms of a probabilistic interpretation. And now today, for this, we'll see a slightly different formulation. So not just the interpretation of how we get to the formula, but we'll see a slightly different objective function that we can maximize, but which is equivalent. And so this will be essentially the same step that we did from last time for the support vector machine. We'll do now here. We'll use slightly different techniques, but again, we'll show you a different alternative representation. In this representation, in particular, important thing will be that it's also what's called kernelized. So it also just depends on this matrix here, K, okay, x by x. And so as last time, okay, one thing is just, while this will change, so you have now 2 formulations. One, the complexity will have something to do with n third. The other one, complexity will have something to do with d third plus something. So depending whether d or n is larger, one might be more efficient than the other one. So that's already one reason. But the other reason to do this, we'll see, is that we then get to what we said was this kernel trick. We'll see that once we have a formulation that just depends on the kernel, and there are many problems can be written like that, then it will be very easy to do what we had often already talked about, namely to extend and go to a larger feature space. And in many cases, we can do this without any extra complexity, right? Remember, what was this extra feature space? You had an x, but you wanted to not just live in x, you wanted to add maybe some other polynomials of it or whatever, some functions of it. So maybe go from a 5-dimensional to whatever, 20-dimensional space. Now, everything is, in general, everything would be in this larger dimensional space. And we'll see today that if we do this in the right way, once this only depends on this kernel here, then we can often go into a much larger dimensional space. We'll see even a case where we can go in an infinite dimensional space, but the complexity is essentially exactly the same. Okay, and so that's exactly what's called the kernel trick, and we'll see what the conditions are. Of course, we cannot just do any feature spaces, or any feature vectors. We can only do specific ones, but this is something that you will come across all the time, so it's good to have heard about it. Okay, so we'll go back, for the nth time to least squares, but now the idea will be that we'll want to write down the objective function in a slightly different way. So remember, typically, that's what we want to do. right? We want to minimize this. And we already said what is the solution, right? So if this is the argmin, and let's call it W star, then we have already written down what the solution is. And one way, or the way we had derived what the solution was, that it was X transpose, this is the big data matrix, X plus lambda the identity matrix times xt times y. Okay, so we can write down the solution in terms of that expression. And this is, of course, again, this data matrix, right? So this was now D times N. This was N times D. So the whole thing here, the N will cancel out, will be D by D. We'll add something else, right? That comes from the regularization term. And then this will be D by D. This is, again, D by N, right? And this is just a vector of size N, right? So it all checks out. At the end, this will be just a vector. OK, so this is the solution that we had written down. And now the claim is that there is an alternative or equivalent is an equivalent way, okay? And the equivalent way will be the following. We can also write W star, or maybe alternative. And OK, so sorry, there's a -1 missing. OK. And an alternative way. And the alternative way is the following. We can also write it down at xt times x xt plus lambda. This is now of dimension n. I, this is the identity matrix, and then the matrix with just identity on the diagonal, and then we're having here y. OK, so now this thing here is an n by n matrix, right? So it's slightly different. This is now n by n. Then multiply this, or get some vector of length n. This is, again, of course, d times n here, right? And so if I multiply this out, I get, again, a vector of size d, right? So the claim is that I have either this formulation here, or I can also have this formulation, right? So let's just convince ourselves that that indeed we can do that. It's quite easy. If you just take two matrices, let's say this is m times n, and let's say this is another one. This is q is n times m, right? So if I write something like p, q, p plus p, okay? So let me write this expression. And so let's just check, right? So this is, so we can, this works out, right? As long as this dimension, I can either from the left or multiply, right? So then I can factorize this, of course, in two ways, right? I can take out p from the left, right? And then I have p, q, p plus I, right? Or I can factorize this from the right, right? I can also factorize this from the right, and then I can also write this as pq plus I times p. Clear? I mean, I can take it out from left or right. So now if I assume that q, p plus I and p, q plus I are invertible, right? If I assume that I can invert this matrix, then I can multiply here by this one here, right? From the right by the inverse here, and I can multiply on the left by the inverse here, right? So then what do I get? Then I get p, q plus I minus 1, and then p. And that's the same as if I multiply this from the right, then I get p, and what do I get? I get q, p plus I minus 1, right? And so now to get back here between the two, you can kind of see, right? So you have this PQP, right? And so here we're having, this is exactly this xt, x, xt, right? So then I should pick the p, to be xt, and I should pick the q to be x. And then there's still this lambda in there. So one of them, you know, I guess I can put in here something like a 1 over lambda, right? And so now if you put this back in, you will see that you get exactly this, this equation here that we have, you know, without the I, right, which just multiplies thing. This will give us exactly the equivalence of the two. Okay, so I haven't really done anything. Okay, so you might ask, what's the whole point? Okay, I mean, what's the point of writing the solution in this thing? Well, okay, there's some points here, right? So, you know, if you look in here, right? So if you multiply things out, what is the major? Oh, again, I have a -1. Sorry. Okay. So, you know, what is the there's of course complexities, right? Once in a while I have this x by x. It's, you know, so this one, it will be an n by n matrix, for example, right? So if I have an n by n matrix, then what is the complexity of inverting an n by n matrix generically if it doesn't have any particular structure? N cubed, right? So the complexity here, right, will be something like O of n cubed, and then there will still be a dn squared term because I multiply things out, okay? Versus here, if I do things, this is d by d, right? So what I have here, the complexity is something like d third plus n d squared, okay? Just quoting the largest terms here, right? So, okay, so there's already a difference perhaps in computation depending if n or d are larger. So there's maybe 1 point. But there's a much more important point. And the much more important point is if I'm looking at this thing here, right? So what does this say? So let's delete this thing on the right. So if you look at the equation for the second, what the W star is, what the optimal solution is, then this tells us something structurally. So we're looking at this. Okay, so let's write it maybe down one more time. So we're having W star yeah, okay, that's correct. And so let me simply call this one here alpha. Okay, so I just call this alpha, is some vector. So let's just see, right? This is d times n, right? This vector is vector of size d. And so then, of course, this alpha here is just a vector of size n. Okay, and it's called alpha is, you know, it's exactly the same kind of scheme that we did beforehand when we did the, you know, when we derived the alternative formulations via duality. So let's look at that, right? So what does this say? This says the following. It says that this vector d here, sorry, this vector w here, the optimum one, right? What are the columns here? The columns here are just the feature vectors, right? So they're just the x1, x2, x3, and so on. These are the feature vectors of length d, right? And so all this one does by multiplying by alpha here is that I'm going to take a linear combination of these feature vectors, right? So it means that the optimal solution W star lies in the row space spanned by x. Right? So I'm writing here x and not xt. This is the xt, right? Okay, so it gives us a And something like this, you know, we just did it now specifically for this, but there's some more general theorems, and these are typically called representer theorems. And they say that for a more general class of problems that have this form, but you're allowed to have here a much more general class of functions, that will be true. Okay? It will be true that it can represent the optimum solution as just some linear combination of the feature vectors. Okay? So that this lies always in the row space spanned by X. Okay, so we know a little bit something now about this, and so this fact, okay, that so let me call this for the specific one, let me call this star. So this fact that the W thing is just xt times alpha star, so this is, you know, for the instance here, this representer theorem, that will be quite important. Okay, so this will play an important role when we get further. Okay, so far all we have done is write this down, the optimum solution, in two ways. And then in this way, when we write it down here, we see that there's some structure to this solution. So now let's look at the optimization problem itself. And so the claim is that there's an alternative problem, alternative optimization problem. And the alternative optimization problem is that now rather than searching for the optimum W, you're going to search for the optimum alpha. And this alpha will be then exactly linked to this W by the xt. Okay, so we're searching for that alpha star such that when I multiply it with xt, it gives me the optimum W. Right? And so the claim is that what I can do is the following. I'm looking at the minimum of all alpha. And now I get something like this. I get alpha transposed. And so now, let me just see, we have xt plus lambda I. And then we're having alpha minus minus alpha transpose times y. Okay, let me just make sure that I get it right. So I claim that this is an alternative formulation. xxt. Okay, got it right. Okay, so the claim is that if I do this, if I define that star and do this, okay, then if I now define W star to be x just according to this representer theorem, right, according to the x transposed times alpha star, that I end up with exactly the same W star that I already had. Okay, that this gives me the same solution. So solving this problem, you know, I mean, I have, of course, already a solution, but if we optimize that one, if we found the minimum for this problem, we would also have solved our problem. Okay, and so why are we interested in this? We are interested in this because if you look at this, this is again our kernel. Okay, the only way that the data, you know, we have the y's in here, but the only way that the features here appear in the data, in the formulation, is again via this kernel. Okay, and so that will be the crucial part. Okay, so how do we see that that gives us the same solution? So the claim is that I plug this in, I should get this W star that I have here, okay? Written up there. We just pulled it out of thin air, okay? But how, you know, if I claim it, how could we check it? I don't want to rederive it. I don't want to see how we got it. I just want to now, once I claim it, sometimes it's much easier once someone claims it to, to check whether it's true or not. Might not be so easy to derive it. We're trying to do a minimum, right? So how do we, what is the obvious thing if we're doing some minimum? What should we do? We take the gradient. Okay, so let's just try to take the gradient of this, right? So let me call this whatever, some L of alpha. Okay, so let me take the gradient of this of alpha. Okay, so someone help me. What do we get? The first term, what will I get from the first term? Right, the only thing that it's just some form here, right? So I will get from both sides this. So all I will get, I get this twice, right? So what I will get is just x transposed plus lambda I times the alpha, right? So that's what I get from the first term. And from the second term, I get minus y, right? Because I take it with respect to. OK, now let's see if we can solve it, right? So we solve this here. So what do we get? We're getting that alpha star, right, is equal to y. Sorry, we have y. And then we're having x transpose plus lambda I times y, right? And so now we claim that this should be the same as this. So now if I multiply this by xt, I have xt plus lambda I times y. OK? Make sense? So the point is simply that remember what we did last time. We had an alternative formulation. And so this we derived by duality. Here we just use something even much simpler. OK, yes, please. I forgot the -1 again. I should have forgotten it. I did forget it all the time. I should not have corrected it, and then it would have been OK again. No? Would have been the same. OK, good. Good. OK, thanks. So the point now is the following, that I have different formulations for the same problem, right? Last time we saw that it can either find the optimize over the W, or we can optimize over the alpha. We have exactly the same kind of formulation here. And we saw that in both of these cases, when we do that, that the problem, what's called, kernelizes it, right? So that the only way that the features appear here, they appear here in terms of this kernel, right? So that's the most important thing here. So note, in this formulation, the features, or the data, okay, the data x, the feature vector, okay, x only appears in the form of the kernel. And so this is some n by n matrix. Right, so this kernel is a matrix. It's n by n. And so here we just have the feature vector 1 times vector, the inner product here, and then x1 transpose x2, and then we're having x1 times transpose xn, and then we're having here x2, right, x1 and x2 transpose x2, etc. Right, so that's the kernel matrix. Okay, so now we are, so now comes we're getting to the trick, okay? And so the trick will be something quite nice. And so let me first write it down maybe slightly more, it says first say the idea, and then I think the easiest one is if we simply look at examples. right? So the point here is that maybe I'm not happy with the feature vector I have, right? So I have a feature vector x, and so that's just some, or the xn's, and that lives in some, let's say, d-dimensional real space, let's say, right? But perhaps it's not good enough, okay? Perhaps my model is not powerful enough. So what we said is, well, take some feature map, right, xn, and now, this will in general be in some, whatever, the twiddle, right? And presumably, typically, we build that to be much larger or larger than the d, right? So we have seen examples, maybe have x1 and x2, and then I add x1 squared, x2 squared, the cross terms, whatever you're interested in, right? So what I could do is, of course, let's assume I'm not happy, I go to a higher dimension, and let's assume I go to a quite higher dimension, right? So what I could do is, of course, I could now do everything I've done, simply replace all the x's by this phi of x's, right? And nothing changes, right? So I have, of course, also for this new problem now, right? I have also a kernel matrix, but now for this new kernel matrix, right? So what I would do is I would compute the phi of x1 transpose times the phi of x1, etc. Right? I'm gonna whatever phi of x2 transpose phi of x1, etc. Right? Now, of course, in general, if I go to a much higher dimensional space, now in general, these products will be more costly to compute, right? If I do this. Clear? Okay, so the question is if there's maybe a way to not ever having to do this, not ever actually looking at this large one. And the question is if I can do all the computation in this smaller space. And so the idea is that perhaps, if I'm lucky, okay, perhaps there exists some kernel function. Okay, so all these things depends now on vectors, so I'm not sure, let me not write it. Perhaps there exists a kernel function. These are all vectors. These are two vectors. Okay, and so you think of this, one of them as this vector, the other one being the other one. And perhaps there exists a function and a feature map such that the following is true, that for whatever this function is, and we'll do examples in a second, and there's a suitable feature map, presumably into a much higher dimension, such that I actually have equality for these two things. Right? So let's assume that exists. Then what could I do, right? Rather than first taking the x, mapping it to this presumably much higher dimensional space, and now doing the inner product to compute each of these entries here, right? I could compute this by just writing, by having the same matrix here, and now having the matrix where I just do the kernel map, right? x1, x1, and the kernel map x1, x2, etc. Is that clear? Since these two are the same, right? There's an equality, the two. And right now, we'll see in a second examples, and then hopefully will be much clearer. But if you had equality, right? If you had just some simple function here of the two, so imagine that this is maybe two-dimensional, and we'll see an example where this is actually infinite dimensional, okay? So let's not go right away there, but let's assume that's two-dimensional and that's 100-dimensional, right? You add all the polynomials of degree 30 to it, let's say, right? So you could take now my two-dimensional thing, expand it to a 100-dimensional thing, right, a vector, and then taking the two vector and taking the inner product. But perhaps there's a very simple function just on the two-dimensional vectors that corresponds exactly to this operation. Okay, if we're lucky, then we never have to go to this 100-dimensional space. We just do something, we do some simple operation over the maybe squaring or taking some polynomials in the two-dimensional space. And if that equality is true, we can just compute it like that. Okay? So let's look at, rather than thinking in the abstract, let's look at examples. Right? So of course, the trivial example is if I pick, so what I will do is now I will kind of go the other way around. I'll pick I'll pick a kappa, and then see whether that corresponds to a phi such that this is true, okay? So of course, a trivial example, right? If I pick kappa x, whatever 1, x2 to be, well, if I just pick it, let's assume this is maybe even over the reals, maybe let's assume even the x1, x2, well, I don't even need to do this. Let's assume I just pick this itself to be the inner product, right? Right, so that's the trivial example. Then, of course, the phi that corresponds to it, right? The phi of x will just be the x, right? I haven't done anything. That's just an identity, right? Nothing interesting happens. Okay, so let's look at some non-trivial examples. Let's pick, what do we pick first? Let's say pick it x. So let's pick, for example, kappa of x1, x2, and the x1 and x2, they are, let's say, over the reals. They're just scalar, right? And now let's assume I pick this to be x1, x2 squared, right? Okay, so this function just takes the two numbers, multiplies them together, and squares it. It's scalar. It's as simple as possible, right? And the vector's origin were already scalar. So what is the original phi of x? Again, a scalar, such that if I now then take the inner product of the two, right, I will get that out. Right? Just the simplest possible one will just be x squared. Okay? So again, not super interesting. Okay, let's do something a little bit more interesting. So let's pick the x1 and x2 to be in R third, right? So we're picking this to be vectors of length 3. And let's pick kappa of x1 and x2 to be, let's see, I need to check. I guess I want something like this. Okay, I pick this. Okay, so I pick it, I'll pick x1, so I pick all possible, sorry, this is not a good notation, terrible notation. Absolutely the wrong thing, sorry. I want this to be what? Let me change the notation here, sorry, because otherwise I have subscripts. Let me pick this x and x prime. And then what do I want here? I want here x1 and x1 prime, I think. I think I want all the pairs. Let me just check. Yes, I want all the pairs. So I want x2, x2 prime, and I want x3 and x3 prime. Okay, and then I want the square. So all I take is I take always the pairwise, I mean just the product, the pairwise product, right? And then I take the sum of this thing and then I square it. Okay? So the question is now, what is the phi that corresponds to it? So, so let's just check. So what kind of terms will we get here, right? So if we expand this out, we're going to get x1, x1 prime squared. We're going to get, of course, the all x2, x2 prime squared, x3, x3 squared, right? But then we're also going to get all the cross terms that we have in here, right? So we're going to get things like 2 times x1, x1 prime, times x2, times x2 prime, plus, and all the possible pairs that we have in here, right? Is that clear? And we get 2 for all of those if the 2 are different. right? So we have 2 times x1, x1 prime, x3 times x3 prime, plus 2 times x2, x2 prime, x3 times x3 prime. Right? I'm just expanding out this square here. So the question is, can I expand? So what did I start with, right? I started with the vector. So the x was equal to x1, x2, x3. The x prime was equal to x1 prime, x2 prime, x3 prime, right? And the question is now, can I write this, can I expand out these vectors, right? So I apply now a phi of this thing. So can I write this now as phi of x being some vector, and we have to see what dimension this would be, right? So that when I then multiply things out, I just multiply them out and now take an inner product in this higher space. I get exactly this expression here. Right, so, yes?
It should be x transpose x.
Yes, so where do I have x transpose? Where?
So what should be x? Can you repeat that?
So what I now want is a phi, something, that only depends on the x, right? Such that I want this to be equal to phi of x transpose times phi of x prime. Right? So I want that this function is representable as an inner product, but in a potentially higher dimensional space. Any guesses? Right? So now, remember, the first one, right, this can only depend on x, and this can only depend on x prime, right? So whenever I have a term here, for example, this one, right, then this one, this one comes from the x, right? So I get here, this is x1 squared, and this is x1 prime squared, right? This must come, so if I have a term like this, presumably somewhere I must have in this phi of x, right? Presumably I must have somewhere a term here, right? Like that. Clear? Because if I take this term and then I take the phi of the x prime, and I have here an x1 prime squared, and then I take the inner product, this will give me that term here, right? So let's try. Okay, so then presumably this is all symmetric, right? So this would be here, x2 prime squared. And then I have x3 squared and x3 prime squared, right? So these three now, if I multiply them together, will give me these three terms, right? So now still the question is, how do I get the other terms? How can I get, for example, this term here? Right, so I have x1, and then I have x2. They all come from x, right? So I have to collect them. And on the other one, I have x1 prime and x2 prime, right? So the obvious thing is that I have here an x1 and an x2. I have the cross term in here. But at the end, it will have a factor 2, but this has to be all symmetric. So better be a square root of 2 in here. And then I have here a square root of 2 x1, x3, and a square root of 2 x2, x3. Right? And I have, of course, the same thing here. These are just exactly symmetric. So I have 2 times x1 prime, x2 prime, square root of 2 x1 prime, x3 prime, square root of 2 x2 prime, x3 prime.
Or maybe instead of square roots, you can have just more coordinates where you will have x1, x2, and x2, x1.
So you could also, maybe with square root, it might be difficult. I mean, you need to split it up. But yes, you could also have several components. Typically, we don't necessarily like to go in a space that higher than necessary. Okay, you can of course always take anything and split it into many terms, right? But that kind of would be the minimal representation. Okay, so This was the first non-trivial example. We'll take now a 15-minute break to process. And when we come back, we go to infinite dimensions. Okay?